So today we're going to be looking at two different little topics. They're pretty simplistic, but they're really, really important. The first is that dipole moment that I introduced to you yesterday. Excuse me, boys, are you ready? Do you have notes out, or are you going to write on your desk? Thanks. All right, so the dipole moment is that little pictorial indicator I was talking about yesterday with the arrows pointing to the more electronegative element in bonds. And ultimately, that's going to indicate the polarity of the whole molecule. And we're going to really focus on that tomorrow. You get to play with model kits tomorrow. It's very exciting. So dipole moment, property of a molecule whose charge distribution can be represented as a center of positive charge and a center of negative charge, meaning you see poles, hence the term dipole. Like I was talking about yesterday, you're going to point to the negative, most electronegative element in a bond, and that indicates the electrons kind of are going in that direction due to the electronegativity. And then we're going to put partial charges on it. What was the little sign I wanted you to use? Lowercase delta, right? Partial positive or partial negative. So looking at the next page, these are some different pictures that describe water. We know water is what kind of molecule, just from your chemistry experience? We know it's a polar molecule. So what I'm wanting you to do in these pictures is to actually, on each bond, go ahead and draw the direction that the dipole moment is going. So here, we know oxygen is more electronegative, so we're going to do an arrow pointing to the oxygen. Don't worry, if you don't put a 2 here, I don't care. That's not necessary. I just want it to be clear that the electrons are really, really, really surrounding that oxygen. Notice in this picture, they went ahead and drew the arrow just from here to here in order just to show that if you think about this molecule, we kind of have one side as negative and one side as positive based on its shape. I'm okay with you, however, just doing one on each bond. And you can see how these, if these were vectors, there's a net. Think of them as force. There would be a net force here, right? Because they're not like equal and opposite direction. So this is what's showing that there is a polar molecule, is the fact that there's a heavy-sided negative side to the actual molecule. This is showing you the electron distribution, where red is your most electron dense and blue is your least electron dense. So looking at this picture, do you see how it's a very heavy red on one side? This also shows you that this is a polar molecule. So yes, our bonds are polar, but our molecule is also polar. If you look at this next set of pictures, carbon dioxide is an example of something that doesn't have a net dipole moment. You can still draw your little arrows toward the more electronegative species in each bond. But think of this as a tug of war, or think of this again as adding vectors. There's no net force, right? No net dipole moment, because these are in equal and opposite directions and then they cancel. What that leads to, take a look at this. Do you see how this is a symmetrical distribution of electrons? Do you see that around, how it's very symmetrical? Now, I'm not saying the molecule is symmetrical, and if you ever say that on the AP, there's going to be a problem, because they're not talking about the molecule symmetry. They're talking about the cloud of electron symmetry. So do you see how the cloud is symmetrical in terms of where we're most electron rich and where we're not electron rich? So what type of molecule would this be, polar or nonpolar? Nonpolar. But what can you tell me about these bonds? Are they polar or nonpolar? They're polar. So my little lesson here is you can have polar bonds, yet based on how they're arranged around the central atom and how many lone pairs there are and all these different things we're going to talk about tomorrow, your molecule could end up being nonpolar. So just know that is a possibility. Okay? There's a difference between polar bonds and a polar molecule. Yes? how evenly distributed the electron densities are if you look at the colors. Okay, we've got, and sometimes something like this confuses. If you see arrows that are pointing equal and opposite directions, these things are the exact same electronegativity. So they're pulling the same strength on the center, like a tug of war. Who would win this tug of war game? Nobody. Okay, so there is no, if you think of these as force arrows, there's no net force at all. So that would show that the whole molecule itself is nonpolar, even though the bonds are polar. Yeah. Yes, it's just the form. It's what they want you to do. Like, did they? Yeah, they have them in these pictures. You can see them here. Like right there, do you see it? It's just a form thing. The reason, I don't know. I couldn't give you a reason. I just do it because they tell us to do it. So each of the following determine the orientation of the dipole moment. So I want you to tell me if there's a dipole moment in the whole molecule, meaning if it's polar or nonpolar. And then we'll talk about the bonds as well. HI, when you're dealing with something like this, which is just a teeny little one bond thing, bond polarity and molecule polarity will be the same because there's only a line, two things attached. So looking at this, which is more electronegative? I. So we're going to draw an arrow to I with this little hash mark, making this side partially negative and this side partially positive. That bond is polar. What can you tell me about this molecule? Polar. There is a dipole moment here because there's only two things attached. So unless they're exactly the same, there's going to be a polarity. Got it? N2, we're going to relearn tomorrow how to do these Lewis structures, but it's a triple bond and it looks like that. Is there a dipole moment here? No, it's a nonpolar bond. Only two things are attached. So this is a nonpolar molecule. So there's no dipole moment. Polar molecules have dipole moments. Nonpolar molecules do not. So, what? Yeah, I mean, they're just a different term. Before we do C, I want to do carbon tetrafluoride, CF4. So I don't know if you all remember this, and if you don't, you're going to get a crash course in remembering tomorrow. Does anybody remember the shape of this thing? Four things attached. Very nice, tetrahedral with bond angles of about 109.5. So if you think about that carbon, this is not planar. The carbon is surrounded by these fluorines. Every fluorine is going to be more electronegative than the carbon, right? So the fluorine, the electrons in each carbon to fluorine bond are residing closer to the fluorines. So we have a partial negative in all of these guys. These are definitely polar bonds. But what can you tell me about the polarity of the molecule? Why is it nonpolar? And I want you to be really careful when you say things like they're equal or they cancel. The fancy way to say it is there's an even distribution of electrons, right, around that center. They're all pulling, or the attraction of the electrons in the bonds is the same in all the situations, totally surrounding this carbon. So there is, again, no dipole moment. But again, we're in a situation, we have a nonpolar molecule, but what is polar? The bonds are polar. Molecular polarity is so different than bond polarity, and it's crucial that you can identify that. Where things change a little bit is when we're looking at something like CCl2F2. Again, because this is three-dimensional, it doesn't matter where you place the Cl's and the F's. They're all around the center in that tetrahedral. So it's not going to be a different molecule if I put an F here and a Cl here. They're still the same distance apart, no matter where we place them. So looking at this, we know we have all polar bonds again, right? But what's different this time? Fluorine, who's pulling the electrons more? Fluorine is. So fluorines, I'm just going to use a size kind of to show the difference. Fluorine's got a little heftier pull on the shared electrons than the chlorines. We still have partial negatives all the way around, and we still have a partial positive here, but because of the increased electronegativity here, there is going to be a definite density increase of electrons on this side of the molecule. And I don't want to say side. Again, tomorrow when you see these in three-dimensional space, you'll know what I mean. But what does this do to the polarity of the molecule then? Make it polar. So the little lesson here is that any time you have different things attached to a central atom, it's going to be polar because they're not pulling those shared electrons at the exact same intensity. Okay? So we're going to revisit molecule polarity tomorrow, and you get to build them and look at them and all that jazz. Questions? Because we're totally changing topic now, like 100% different. All right. Now, just because it's kind of an odd thing and I never know where to put it, I was like, today's a short day, so let's just shove it in today. And that's finding delta H of a reaction. Up until this point, think back to the thermo unit. What were the ways to find delta H of a reaction? Big Mama. Flippy thing. One more. We did it in the lab. Calorimetry, we found Q, and then what do we do? How do we convert it to delta H? Negative Q is equal to delta H, exactly. So what we're doing today is we're adding another way to find delta H of a reaction, and that's using bond energies. What we're actually going to do is from a table of bond energies, meaning there's going to be a table, and there's going to be the energy required to break each bond on that table. And we're going to find the sum of the bonds broken minus the sum of the bonds formed. This is actually a revised Big Mama, and I'm going to talk about that in a second, but I want to just do it cold as broken minus formed. I need you to memorize bonds broken minus bonds formed. How is this different than Big Mama? What is Big Mama? Products minus reactants. So if you're breaking, you're really doing reactants minus products, but that is done for a reason, and I'll explain it. All I need you to do is just accept bonds broken minus bonds formed. This is an example. We have bond energies, and then we have a reaction usually drawn out in such a way that you can figure out the structure of all the reactants and products. So what we're going to do, I'm just going to redraw this guy so to make sure you can see all the bonds, and it's going to make this. So what we're going to do is we're going to break all these bonds, and we're going to subtract all the bonds that we form. So bonds broken. You literally count. How many C to H bonds are we breaking? 3 C to H's. C to H value is 413 from the table. What else are we breaking in this picture? 1 C to N single bond. 1 C to N is 305. And what else are we breaking? Triple bond N to C, that is 891. Okay, so these are all the bonds broken. We're going to sum these, bonds broken minus, and now let's write down all the bonds we are forming. What are we forming? I see the 3 C to N's, right? What else are we forming? Look at the picture. How many? 1 C to C, and we're forming, again, one of these. If you get really good at this, you can just leave out the things that aren't changing, but sometimes that leads to a little bit of confusion, so I'm almost of the opinion you should just do all the bonds, break all the bonds, and remake all the bonds. Okay, so bonds broken minus bonds formed gives us a delta H of negative 42.0 kilojoules per, so that's an exothermic reaction. So that is the delta H of this reaction up here. Then we could take that delta H and do different things with it. We could find the heat of formation of one of these, or we could end up finding the entropy or free energy of one of these. This is usually like the first step in a really long thermo problem, because we're going to do a second part of thermo next semester. Now, why is this Big Mama? This is Big Mama. But here's the thing. Notice all the signs on this table. Notice all the signs are positive, right? Okay. Now, if you are really struggling in this class or don't like math, I want you to cover your ears and put your head down and don't listen to me right now. Okay? If you like math, I want to explain to you why this is Big Mama. Broken minus formed is Big Mama because we're taking account the signs of the breaking and the forming. When you break the bond in the system, bond's broken, what is that? In terms of energy, positive or negative? Positive. When bonds are formed, what is the energy? Negative, because energy is released. Now, remembering Big Mama is products minus reactants. Products are these guys. What did we do to these? We formed them, right? So if we formed them, what should their sign be? Negative. Their sign is negative. So if we were going to use Big Mama using this, we would have to make all of these negative by hand. And then we could say minus products minus reactants. Reactants are things that we broke. So that would be positive. So we would have to do a sign change for reactants or products differently. That is a huge pain. Not to mention you're going to get confused. So what broken minus formed does is take that sign into account and puts you in a situation where you're doing mathematically the exact same thing, but all you have to do is take all the values positive straight from the chart and put them in. Does that kind of make sense? That's why it's flipped. I graded this question a few years back, and so many people, I don't even know if I graded any of them that were right. Majority of the people did products minus reactants, and they got the wrong sign. Because, yeah, they did products minus reactants, but they didn't make the formed negative or the products negative like they were supposed to. So they got the wrong sign. So just remember, if you have bond energy, it's broken minus formed every single time. So let's do a couple practice problems. So right here, we have another bond energy table. Notice all the values are positive. One thing I do want to point out, this is going to be similar to the table on your test. This is actually the exact same table on your test. Down here, there's a little asterisk that goes with this guy. This is a C double bonded O. In everything but CO2, you use 745. However, the C double bond in CO2 has a different value of 799. So make sure if you ever get CO2, you use this value. Well, and it'll be times 2 because there's 2 of them in CO2. But just watch yourself on that. So let's practice how you do this. We're going to do using bond energies. When you see that, what do you think? When you see this, broken minus formed. Literally, that's all you'll ever do with bond energies. So what are we breaking here? 4 CHs. So look up CH. Tell me what it is. 413 plus, and then we're breaking what? 2 O double bond O. How many is that? 2 of those. So those are my bonds broken. Minus. Now be careful, we're in CO2 here, so we're breaking 2 799s. We're not doing the 745 one. We're doing the one at the bottom of the table. How many Hos are we breaking? Yes, I said Ho. How many? 4. We have two in each, right? But we have 2 molecules total. So what's the value for our Ho? $467. Okay, so go ahead and calculate that. Broken minus formed. No, because the value on the table is for a double bond or a triple bond or a single bond. Okay? Negative 824. Anyone? I need a second because people have been making mistakes this morning. Negative 824 kilojoules per mole is the delta H of that reaction. This one is a typical one as well. The difference here is you have to actually draw your Lewis dot structures. Again, tomorrow we're going to revisit how to do this, but this is a triple bond. So you have to know the Lewis dot structure before you can really do this, because you can't assume that's a single bond. You'll get the wrong value. H2 is single bonds, and there's 3 of those. Does anyone remember what NH3 looks like? There's 2 of them. We have 8 NH3s, and then we have a lone pair there. So there's 3 NH bonds that we have to break. Okay. So 1 N triple bond N. What is that value? We're doing bonds broken. (941 kilojoules per mole). Well, I don't need the units. We'll do that at the end. Plus 3 HHs. 432. All right, that's broken, minus how many NHs do we have? 6 NHs. There's 2 molecules, but there's 3 NHs in each. So N to H is 391. All right, so let's go ahead and calculate our delta H, broken minus formed. Negative 109, yep. Negative 109 kilojoules per mole. And that is our delta H for that reaction. All right, so now we're going to have a little bit of a contest. The first one to get the answer to this next one, oh, God, gets a sticker. Damn it. Did y'all see it? Okay, so we're not having a contest now. I'm a little mad. However, you need to do it, because I promise you, you're not going to get that answer the first time. Well, now you might, because I circled something. Yeah, that totally disappointed me. Everyone do this problem on your own right now, and make sure you get negative 2881. I'm turning the video off. This is the answer. That's it. I'm done. Goodbye.